Hello everyone, this is Josef Not here and welcome back to the second part of this tutorial where we are doing our first simulation in OpenFoam. Now in the first part we did a lot of things. I showed you the case setup, what it looks like with zero, constant and system. I showed you also the initial conditions, the initial values, the boundary conditions, then the viscosity where you can set the viscosity, and then simulation controls, how to set the end time, for example. I also showed you the source code. The equations that are being solved in this solver, and also the boundaries, where you can define the boundaries and that they have to match here and here. I also showed you the results with the first triangular mesh. And I imported a quad mesh from this mesh file. And I was about to start the simulation. And now let's do this. I already changed the end time to 75. Now I want to mention here that you can save in Nano with the command Ctrl O, enter, and you can exit with the command Ctrl X. Now let's come to the simulation. I type in OpenFoam and press enter, and the simulation is running. Let's wait until it stops. It takes a little bit longer because we have a different mesh. But it finished now, and you see, for example, the maximum corona number is at 0.6, so there is a difference, which is the mesh, of course. But then we see the number of iterations are the same because we left the settings. And now let's just open up the results. Good. So I will do that here in this paraview. I open up, I go into the quad folder, and I could just go to all files and control and then OK, but this, if you want to do this all over and over again, this is a real pain in the butt. What you can do is you make a copy. Let's just go into system, and you can create a file with the extension of .foam. You can just copy, for example, your control dict to control dict.foam. Now you have your control dict and this file. And if I go now to elbow_quad and system, here you see this control dict.foam. I click OK. And now I have it, paraview loaded it, and I click on apply. And now I have my results. But unfortunately, the quad mesh has a different location than the triangular mesh. So I have to shift either one of them. So I will shift this triangular mesh, and I will have to move it in the negative x direction and the negative y direction. You can translate it in paraview directly, so I will move it, let's say, by -10 to 5. No, that's not enough. 75. No, that's still not good enough, so 120 maybe. Yes, this is better. And then I will move it by -50, that's too much. -35, -30. Okay, that's good enough for me. Good, now we are at the time 0. Now we're at 1. I rescale and I show you now the velocity. Now here you see the difference between the meshes. This is a triangular mesh and this is a quad mesh. And if I blend out now, here you see that you do not have these triangles anymore. And if I go to the very last time step and I rescale according to this case, here you see that we can depict with this mesh a certain backflow here, which we cannot do here. And here the results are very diffused regarding the velocity, and here this is depicted in a better way. Let's just say that. And here we also kind of depict a backflow. So this is better, but still not good enough for me, and this is the reason why I do the third simulation in elbow_quad_refined. What do we do here? We import the quad mesh and we will refine this quad mesh. Let's just do that. Again, import it with Fluent Mesh to Foam, elbow_quad.msh as before. And now we refine this mesh with the command, you will guess it, I guess, refine mesh and then space minus overwrite. Minus overwrite will overwrite if I go back here. So we are here. Now we imported our mesh files, and this command will overwrite these files with the files of the refined mesh. So I press now enter, and it says it's a 2D case refining in directions X and Y, and this is exactly what we want. Now, what I will do, at first I want to change, of course, the end time, and now instead of nano I will show you an additional alternative for an editor that you can use in the terminal called VI, and I will use the Vim version. So VIM space system control dict and then enter. This opens up the control dict again in the terminal. Now you can only use the cursor again, and I want to change here the value. Now I have to press A in order to insert something. Now I am deleting 10 and typing in 75. And I also want to decrease the delta t by a factor of 2. I press escape and I save it by pressing :WQ and enter. And now if I open it up, now it's saved. Now the reason for the smaller time step is actually this Courant number, because in the Courant number you have your time steps, and by decreasing the length of your cell you have to change also your delta t, but I will come to that in a later tutorial. Just believe me that I have to do this. And now I can, but no, I forgot to do something, because I decreased the time step by a factor of 2. Of course I have to increase, typing A, increase the write interval, because I want to save after 1, 2, 3, 4, 5 and so on seconds. Escape and then :WQ, enter. And now I type in OpenFoam, enter, and now the simulation started. This will take a while, so I will stop recording and come back when the simulation stops. Okay, now the simulation stopped. It ran until 75 seconds. It took a little bit longer. And now you see that the maximum corona number is 0.83, so there is a definite change. Now, let's just open up this case. I showed you how you can open up the case by clicking on Control Dict and then OpenFoam OK, or you rename your Control Dict with the extension .foam. There is another possibility to convert your results into VTK format and then open up the VTK files. I show you how you can do this. You type in foam to VTK with a capital T and capital VTKs, pressing enter, and this will convert your results into VTK format. And what is happening is that you have now a VTK folder where you have your results, your files. And you can open this up, quad refined, so now I just opened it up, apply. Now this is here, it has the same location as the second case, so I have to translate it. In the positive X direction I will try 120, it's too much. Maybe 75, yes, looks okay. Okay, so now the third one is in the middle, velocity. And let me just show you the meshes. For that I will go to solid color and then surface with edges, and this shows you the mesh, and you see that this mesh is much finer than the two meshes here and here. Now let's take a look at the results. What's the difference? If I blend out the meshes, go to the last time step, and for example the velocity. Okay, now what's the difference here? You see that this velocity maximum here is depicted very nicely, and it's not so diffused as here and here. And indeed, I was correct here. We do have a backflow here and here also. And with this mesh we can depict this. We cannot do it with this mesh. So this is the reason why it is very important to think about your calculation grid and the quality of your mesh. Obviously, this mesh is not very good for that. In order to depict large scales that the velocity is going here in the positive X direction and here in the positive Y direction, and then here something's happening, then this grid is good enough. But in order to depict details like this backflow or the velocity maximum here, then you really need a better mesh. This is the reason why I want to show you. And in a later tutorial we will come back to grid convergence, where I will show you exactly this phenomenon. Now I want to show you a couple of things here. For example, if you want to make a screenshot, you can just make a screenshot through Ubuntu, but you can actually do it in ParaView. For that, I will show you this edit color map here. You can change this here by clicking on rescale to custom range. For example, you can type in here 0 and go until 4, because why not? Now change to 4, very good. And by clicking this button, you open up this window, and then you can just say velocity and then meters per second. We give it in meters per second. I delete it, and I can change here the font type, for example, times, and then the font size to 10, and additional settings. I say OK. You can move this here to the bottom, and with the middle mouse button you can move your geometry in ParaView. By scrolling your mouse you can zoom in and you can zoom out. Okay, and let's say I want this picture. Save screenshot, and I could change the resolution, but I will just leave it like that, and I will save it not in elbow_3 but into elbow_quad_refined. Yes, and let's just call it velocity, and you can change the type of the file. I use PNG. Okay, and if I go into the folder, now you see that here is this PNG file. I open it up. Now, okay, now we have our PNG file here. And this is actually what I wanted. This is what the PNG file looks like. You can include this in your presentation, into your report, into your thesis, where you want to do it. Now, another thing, what I wanted to show you, how to export diagrams. There are different possibilities. I will show you how you do it in OpenFoam in a later tutorial. But now I want to show you how to do it in ParaView. And for that, you go here to filters. And then in filters, in data analysis, there is this plot over line possibility. I click this. And what this does, this places a line here. You see this line throughout your geometry, and you can move the endpoints of this line here. And I will do that. You can just drag with the mouse, but this is a little bit difficult here in ParaView. It's a better idea to move it here with these points. I will move this end to here. So plus 20 maybe, yeah, more or less, 22. Yeah, that's better. I will not move the Y because I want to start here. This is correct. I will move the Z direction into the center. And I will move this back a little bit to here. Let's try 30. Yes, this is good. And I will not change this. I want to go until the outlet, and I will change this to the center, and let's just use 1000 points along this line. I click apply, and what's happening? ParaView opens up all the possible values that you can plot. I do not want to plot the cell ID, so I unclick it, and now I only plot the p-value, the pressure divided by density, and my velocity magnitude. And this is what it looks like along the line that we defined. I could also plot only the x direction, for example, of our velocity, but I'm not interested in that. Now the question is, how do you export this? Having selected this window, you go to File and then Save Data, and then I go into Elbow Quad Refined here, and I save it as a CSV file so I can open it in LibreOffice. You can open it up in Excel too. I will call it data, for example. OK. And I could write all time steps, but I will only save it for the last time step, and precision of 5 is great. Points is also good for now. OK. And now we have here this data.csv, which I will now open up in LibreOffice. Let's wait for LibreOffice to open. Very good. Now open. And I want to go into OpenFoam and then the correct tutorial, incompressible icofoam and elbow_quad_refined. And here we have the data.csv that we just exported. And yes, this is the correct format. And now here we have our results. Pressure divided by the density, then the x component, the y component and the z component of our velocity, then cell ID and another value. Then important is this arc length. This is the coordinate along this line. So here it's 0 and here it's, let's see, it's 69. And then we have the coordinates. But we are not interested in that, so I will delete these. I will delete these two and also the z component of the velocity, because we are only doing a two-dimensional simulation. And I will cut this and insert it here so I can plot the pressure divided by the density and the velocity. And if I want to plot the velocity magnitude, I have to calculate it. Like this. And this is the velocity magnitude. Very good. So let's just plot the pressure divided by the density. Okay. This is what it looks like. And let's take a look at the velocity. And here you can see the velocity along the line. Let's just make it bigger. That's what she said. Okay, so here you have the velocity along the line. You can make a screenshot of that if you want and include into your thesis, into your report, into your presentation. Now, what I would suggest to do the same for the tree mesh and for the quad mesh. Export it from ParaView, open it up here in LibreOffice or in Excel or in GNUplot or in Origin, wherever you want, and then compare the results. And I can promise you that you will see a difference. And this will be a very good homework for you in order to get familiar with ParaView. So, this is the end of this tutorial. We learned a lot of things today. How to set up a case, what the case setup looks like with the zero constant and the system folders, how to import a mesh file, elbow.msh, elbow_quad.msh, and how to run the simulation, how to change the end time to 75, then how to open the simulation results in ParaView, and I showed you how to export a PNG file and a CSV file from ParaView. Now, this concludes the second part of this tutorial and the tutorial itself. I hope that you enjoyed it and that you learned something. I would like to thank you, and I hope to see you next time.